Yeah, so in terms of composition, cement is composed of uh, a few major oxides like calcium oxide, silicon dioxide, aluminum oxide, and iron oxide. As you can see, the primary composition of cement is in terms of lime or calcium oxide. We have nearly 2/3 of cement is composed of calcium oxide. Apart from these four major oxides, you can also have significant quantities of magnesium oxide, depending upon the source of your limestone, of course. And there are alkalis present to the tune of about 0.3 to 1%. More typically, what we see in Indian cements is that the alkali contents are around 0.6 to 0.8% in India. But several cements could have higher than 1% also. Okay. There are some problems with very high alkali cements, which of course we'll discuss in the course of this series of lectures. Cements abroad typically tend to have a higher alkali content. Now, alkali content in cement helps to actually enhance the early age strength development of the cement, and that's why one has to be very careful about balancing this well. Now, where are these alkalis coming from? Mostly what happens is these alkalis are present in the raw material in the form of alkali sulfates. Alkali sulfates are usually present as impurities in the raw materials, and these basically come into the mixture, compound mixture that we actually have, right. So, the sulfates that are indicated here are not just from the gypsum that we add in the final stages, but also could be from the alkali sulfate sources that are available as impurities in the concrete, in the raw materials. Now, in the kiln, as we discussed earlier, there is going to be a combination of these oxides to form the primary phases: tricalcium silicate, dicalcium silicate, tricalcium aluminate, and tetracalcium aluminoferrite. And if you look at the overall composition, if you add up your C3S and C2S together, typically around 80% would be C3S plus C2S, irrespective of the type of cement. We will talk about different types of cement, but in all cements, if you combine C3S and C2S together, it will be more or less close to 80%. Again, C3A plus C4AF together will be about 12 to 15%. Okay, 80 to 85, let's say, 12 to 15%, and gypsum is around 3 to 4%. That's the amount of gypsum that is available in the mix that we have. Okay. And of course, as I said, in OPC, up to 5% of additives or performance improvers are permitted. Okay. We also spoke earlier that the performance improvers typically are limestone or sometimes fly ash. Okay. So, these are lowering the overall CO2 impact of the cement. But later we learn that at this 5% level, they are also able to provide additional benefits. Okay. Right. So, as far as cement is concerned, C3S is the major component in cement. More than 50% is C3S, and C3S is also responsible for early strength development, right. Now, of course, in projects, people used to be happy to wait for years earlier, right. When we built our old monuments, those were built over years, right. The monuments did not come up in like 3 months or 2 months or 1 year or 2 years or whatever. People used to wait years for monuments to get constructed. As time passed on, we wanted to speedily construct and finish things fast. So, nowadays you have monuments and structures that are produced or constructed in very little time. And because of this, the importance of C3S as a component of cement is only increasing, because C3S is the one which leads to early strength development. Okay. And this early strength development comes from the fact that C3S has a high reactivity because of its irregular structure. We saw a picture of cement clinker earlier, in which C3S had an irregular structure, polygonal structure, which leads to a high reactivity. Okay. And high reactivity also means it has got a high heat of hydration. What do we mean by heat of hydration? It is the heat liberated when cement reacts with water. So, cement is composed of different compounds. So, the heat that is liberated when cement reacts depends on heat liberation of individual compounds. The compounds that react faster liberate a lot more heat. Okay. You might have seen this with lime, right? Slaking of lime. We typically add water to calcium oxide. There is a massive heat evolution that happens from that process. Same thing, Even here in cement also there is an exothermic process which releases heat. Of course, in terms of crystal structures, this is not the right platform for the discussion, but yes, several crystal structures are possible with C3S, and as we were talking earlier, alite is nothing but impure C3S, which has other impurities. Some of the impurities are provided here just for your understanding. We are not really going to discuss this in more detail. C2S is a less irregular structure that's more rounded, as we saw from the pictures of the cement clinker that I showed earlier, and because of this more regular structure, it's got less reactivity. Okay. Overall substitutions of oxides can be up to 4 to 6%. So, in B-lite, C2S can have impurities in the form of these oxides, and again because of the formation and the presence of different types of impurities, the polymorphs exist. There are different forms of, different crystalline forms of C2S or B-lite that may exist. C3A and C4AF, as you saw in the pictures earlier with the clinker, they are not that easy to distinguish as compared to your C2S and C3S, which are much larger crystalline particles. C3A and C4AF are also crystalline, but they are small enough that they are present almost in an intermixed kind of a fashion. Again, in terms of crystalline composition, pure C3A will have a cubic structure, but with impurities it can also get other crystal forms such as orthorhombic. The issue with C3A is it's got the highest heat of hydration. Okay. Amongst all cement compounds, C3A has the highest heat of hydration. So, if you were to produce a low heat cement, what would you do? Reduce the C3A and preferably also reduce C3S, because C3S also liberates a lot of heat, it reacts fast. So, if you have to produce a low heat cement, right, what applications would you need low heat cement for? For mass concrete, dams, right. In such cases, you need a low heat cement, and such cements are produced typically with lower C3A and C3S contents. Okay. C4AF is not really a component that matters too much in the long run, except that of course, to keep this balance of C3A and C4AF, like I said, when you want low heat, you reduce C3A, but when you reduce C3A, the C4AF content will get pushed up slightly. So, it does that balancing of the aluminate fractions in the cement, but otherwise it does not really have a major significance with respect to the hydration reactions. Okay, you will find even if you take a cement which is or concrete structure which is like 50-60 years old, if you take a small microscopic image from inside, you will find that much of the C4AF is present as it is in the original cement. It is not reacted at all. That is because iron is present, and this iron makes it highly insoluble. Okay. So, cement particles have to first start solubilizing and then they react. So, C4AF is a phase that does not solubilize easily. As a result, you will not find the iron particles having, or C4AF phases having reacted much even in concrete that is very old. Okay. So, there are several ways of classifying cements. I am just giving you some principal classifications based on ASTM, Indian standards and European standards. ASTM classifies regular cement, which is as per the ASTM specification C595, into 5 types. One is general purpose, which in India we call as ordinary Portland cement, right. And then type 2 is moderately sulfate resistant and moderate heat of hydration. Essentially, this means lower C3A and C3S. Okay. Then you have type 3, which is high early strength. How will you increase the strength of cement? You increase more C3S, right. Any other way in which you can increase strength gain rate of cement? You can grind the cement finer, right. Increase C3S, finer cement. So, more C3S and finer. And then you have type 4, which is low heat of hydration or low heat cement, right. So, obviously here lower C3A and C3S. And type 5 is sulfate resistant. If you, when we discuss about mechanisms, you will see that sulfate resistance especially is brought about by the fact that you use a cement with lowest C3A content. The aluminate content is reduced to the lowest level in the case of sulfate resistant cement. Okay. So, these are the general ways of characterizing ordinary cement. Of course, in ASTM they also include some air entraining additives in the type 1 and type 2 cements and simply call it type 1A and type 2A. Okay, just to give you this same thing in a snapshot of the compound composition, you can clearly see here that compared to type 1, type 2 has lower C3S and C3A. Type 4 also has lower C3S and C3A, but the C3S lowering in type 4 is much more than in type 2. So, obviously, when you lower C3S, you increase C2S. The silicates typically will add up to nearly 80 to 85%. Okay. So, if you are lowering C3S, you are increasing the C2S. And then type 5, as I said, lower C3A and sometimes also lower C3S as compared to type 1 cement. So, this is the overall chemical composition, which is quite similar if you look at other standards also, like BIS also has a sulfate resistant cement, BIS also has low heat cement, high early strength cement. Most of the characteristics are quite similar across different standards, right. So, this is just putting in words what we just discussed. Then of course, there is also blended cements, about which this course will have a lot of discussion about how materials from other industries like fly ash and slag can be blended along with cement to produce very interesting cementitious properties. So, Portland blast furnace slag cement, in India we call it Portland slag cement, PSC. Okay. So, in the US they call it type 1S, and slag content typically in that is 25 to 70%. Okay, there is a reason for this, and the reason is that slag on its own has a significantly large potential to react. Only problem is it is too slow to react on its own. It needs the presence of cement to exhibit its hydraulic reactions. Okay. So, as a result, slag content permitted in slag cement is quite high. Typically, around 50 to 60% is used, 50 to 60% slag is used in slag cement. That means the cement component or clinker component is quite low, 40 to 50%, right. So, what does this mean? Again, slag cements will have a net lower CO2 potential, emission potential. Okay. So, it is always of benefit to use slag cement from that perspective, and later when we talk about slag in more detail, you will also learn that it is beneficial to use slag cement from also the perspective of higher durability in coastal conditions. We will talk about that later. Portland pozzolan cement is type 1P, and pozzolan content is 15 to 40%, and that is because pozzolans cannot react on their own. They need the lime that is generated from cement hydration. So, I will talk about that just a minute. So, lime is calcium hydroxide. That is what it is written as in cement chemistry. Calcium hydroxide is written as CH or written as CaO dot H2O. That is why we call it CH. So, pozzolans are basically reactive silica, right. So, they combine with CH to give CSH. CSH is calcium silicate hydrate, which is a principal binding component of cement hydration products. Okay. So, you get additional CSH, and that leads to refinement of your porosity. The pores that are in concrete become finer and finer, which makes concrete more durable in the long run. So, it is always durability. Strength is only a secondary factor. Primarily, you want to use blended cements for durability. Okay. And that is the emphasis that we will also give later when we discuss about mineral admixtures. BIS, again, as I said, we have a similar classification. We have general purpose cement or ordinary Portland cement. The only difference is our ordinary Portland cement we further divide into strength classes 33, 43 and 53 grade cement. Okay. And here this grade simply implies the strength achieved by the cement mortar. What type of cement mortar? It has to have a certain specified water content that is determined from the consistency of the cement. Okay. If you remember your testing of the cement that you may have performed during your undergrad days. So, there is specific consistency of the cement, that means the water demand, and based on that you decide the water content to be used in this mix, and you fix the cement to sand ratio as 1:3, right. Prepare a mortar and prepare 70 millimeter cubes and test them at 28 days. You should get this grade 33, 43 or 53. Now, these days 33 is almost not available at all. You only get 43 and 53 produced by the cement companies. Okay. Then just like the ASTM case, we have low heat cement, we have rapid hardening cement, Portland pozzolan cement, Portland slag cement. There is also a sulfate resistant cement in BIS. The only problem is many of these special cements are not always available. Many of these special cements are not always available because cement manufacture is a complicated process. For them to continuously change their batch to produce other types of cement becomes a low value proposition for many of the cement companies. They would like to produce the same cement day in and day out, because then they don't have to readjust their process too much. Like for a company to suddenly start producing low heat cement would require a dedicated kiln, right? Because the processes could be quite different, raw material combinations are different and so on. So, it is not easy or profitable for a company to continuously change the type of cement that they are producing. So, here because these special types of cement are not easily available, the role of the mineral admixtures or mineral additives or supplementary cementing materials becomes all that more paramount. That is where they all come in. For instance, low heat cement, right? If low heat cement is not available, how do you start making concrete for dams where you really have to control the heat evolution? There you go for substitution of cement by what? Fly ash typically. We use fly ash to reduce the heat of hydration because fly ash is extremely slow to react. And if you substitute cement in large quantities with fly ash, you will substantially reduce the amount of heat generation. Okay. So, like that we need to make do with mineral additives whenever we need special properties, like high early strength for instance. If rapid hardening cement is not available or is not very practical to be used, because it may also start setting very quickly. So, it will reduce the time that you have for concreting. Like in Mumbai, you know, right, we have high rise buildings where people are using even M90, M100 cement or M90, M100 grades of concrete. In such cases, imagine using a rapid hardening cement, you will never be able to maintain workability. Okay. In such cases, what comes to benefit of the concrete producer is the use of fine additives like silica fume or metakaolin, about which we will learn more detail later. But all of these compounds are very important from the perspective of producing special concretes, which cannot be achieved because your special cements are not easily available. Okay. So, all these have these are not just technical reasons, economic reasons also are there why these are not easily available, because it affects the profitability of the cement manufacturer. Okay. EN again similar, but EN has a much more diverse classification of cements, right. So, they talk about CEM 1, 2, 3, 4 and 5, where they talk about Portland cements, composite cements, blast furnace cements, pozzolanic cements, and they have composite cements which have much larger levels of substitution. So, if you look at the description, it can be quite difficult for a person who is not well trained in understanding cement. So, the EN standards are meant for engineers who have a high level of understanding of this entire scheme, and because of which they can actually now make concretes that are niche concretes which have very specific blends of cement used in their formulations. Not the same in India. In India, the understanding of the cement is not as good with the civil engineers that are available on site. We are familiar with ordinary Portland cement, but beyond that, even admixtures, mineral admixtures sometimes are out of reach of many people. So, we need to be careful when we we classify cement in too many categories. The problem is then that we have difficulty deciding which to use when. But in Europe, the degree of understanding with these special cements is very good, and they have very well trained people, concrete technologists who can actually understand what each of these cement is. So, what I wanted to say is, those of you who are working in industry, convince your bosses to hire more concrete technologists, because ultimately such decisions about choice of materials, about design of concrete for particular combinations, for particular applications, this is in the hands of a concrete technologist, right. You need to understand cement and concrete in order to be able to get maximum benefit out of all of these materials. Anyway, I will come back to that discussion sometime later. So, this is the overall table that is present in the EN standards, it can be quite complicated to understand, but then once you start understanding what each of these extenders or supplementary materials is coded as, then you can definitely understand the scheme of classification here, but we will not look at that in more detail.